Hello and welcome to week 6 of Algebra. So at this time, please make sure you've got your math notebook out and you're ready to take good notes. Remember, taking good notes is going to help you in the long run. It's going to help you understand the material better and give you something to refer back to as you go to do this week's assignments. So we're going to start with the warm-up, and you're going to complete this warm-up in your math notebook. The warm-up we're going to do is going to get us ready for Unit 2. So we are starting a brand new unit, and this warm-up problem is actually going to give you some insight as to what you're going to be seeing in Unit 2. And one of the things that you're going to be seeing in Unit 2 is we're going to be working on graphing situations. So we're going to take a situation and turn that situation into a graph that shows a relationship over time. And in order to graph those situations, we are going to be identifying key terms and such as stays the same, rises, drops, slows down. So these are some terms that we might see in situations, and in order to graph them, we need to be able to identify what these terms mean, whether they mean something's increasing, decreasing, or staying the same or constant. So what I want you to do is match these four words or phrases with whether they're showing something that's increasing, decreasing, or staying the same, or which is the same thing as constant. So go ahead and click pause and try this warm-up on your own, and then when you're ready to check your work with mine, go ahead and click play. All right, so stays the same. Does that phrase represent something that's increasing? No. Decreasing? No. Constant? Yes. Something that's staying the same is remaining constant. It's not changing. It's not going up and down. It's just staying the same. It's constant. What about rising? Something that's rising is increasing. What about something that drops? Well, drops is another word, just another way that we can show something is decreasing. And then slows down, well, it's not speeding up, so it would be decreasing as well, decreasing. I'm going to move on to the next slide, so if you need more time, go ahead and click pause. All right, so as I mentioned, jumping into Unit 2 this week, and in Unit 2, we're going to be learning about relations and functions. So this week, specifically this week, you're going to be learning how to graph relationships. So Unit 2 is about relations, I mentioned. So how can we graph relationships or situations? We're going to learn this week what is a function, as well as how to determine if an equation is a function. So let's jump right in and take a look at graphing relationships. So we can graph relationships. Sometimes it is introduced as a situation where we're given a situation, just like on this slide, and we can take a situation and graph it by looking at the relationship between two different factors. So in this example, we're given a situation where we are comparing temperature over time. So I'm going to go ahead and mark that down. And while I'm doing that, go ahead and read through this situation. And then we'll read through it together. All right, so the situation says the air temperature increased steadily for several hours and then remained constant. At the end of the day, the temperature increased slightly before dropping sharply. Create a graph So we're going to create a graph that best represents this situation. So again, we're graphing a relationship between two things. And in this case, we're relating, we're looking at the relationship of time and the temperature. How did the temperature change over time? And we can pull out those key words that we just went over in the warm-up, pull out some key words that tell us things like increasing, decreasing, or remaining constant, and put together a graph that relates the temperature over time. So let's go ahead and do that. So let's read through this again, and this time let's highlight some key words that tell us whether the temperature is increasing, decreasing, or staying the same. So it says the air temperature increased steadily. All right, so it's increasing steadily for several hours. Then it remained constant. At the end of the day, the temperature increased, that's another keyword telling us what it does, slightly before dropping sharply. Okay, so let's now decide what these key words mean so that we can graph this relationship. So what was our first key word that we can use to help us graph this situation? So we have highlighted increase steadily. So I'm going to write that down in this little chart. And what does increase steadily mean when it comes to graphing something? Well, it means it's increasing, right? And it's increasing at the steadily, so it's increasing at the same amount over time. So it can look something like that. What's our next key word? And then it remained constant. Constant is our next key word. And constant, so what does constant mean? So constant means it remains at the same temperature. It means it's not increasing or it's not decreasing. So we're going to have a horizontal line to show that the temperature is remaining the same. It's staying constant. So that horizontal line shows us that. The next one is increase slightly. And we know increase slightly means going up again. It's not increasing drastically, so we can show like a small slope to show increasing slightly. And then the last term we have is dropping sharply. And that means decreasing at, our slope's going to be pretty dramatic to show that it's dropping sharply. So now let's put this all together on a graph to show the temperature changing over time. So we start with our increase steadily, and then remember our temperature after several hours remained constant. So we're going to draw in our horizontal line to show that it remained constant. At the end of the day, the temperature increased slightly. So just a little bit of a slope to show increased slightly before dropping drastically, dropping sharply. And we'll show that by this, going down. So this graph relates the temperature to time, and we were able to graph that showing, pulling out those key words and turning it into a graph so that somebody could look at this graph and be able to describe the changes of the temperature over time just by looking at this graph. They wouldn't need the words. And before we move on to the next slide and look at a different type of relationship, I'd like to present or tell you guys that this graph is what we would call a continuous graph. And it's continuous because we never picked up our pencil, right? We could draw this entire graph without picking up our pencil. There's no gaps, there's no holes in this graph. So because there's no stopping points, it's one continuous line, we call this a continuous graph. So this would be an example of a continuous graph. Now let's go on to the next slide where we've got a different type of relationship. It wouldn't be considered continuous. So let's look at this type of graph where we're going to compare the number of weeks and the number of words that somebody can type per minute. And notice how I did that. I came down here before I even read through this situation. I came down and I looked at this graph and I looked at the labels of our X and Y axis, and that really allowed me to see right away what this situation is all about and what two things we're comparing. So just by looking at labeled axes of graphs, it tells us a lot of information about what we're looking at. So let's come back up here and read through this example. It says Jamie is taking an 8-week keyboarding class. At the end of each week, she takes a test to find the number of words she can type per minute. She improves each week. So these points are telling us after each week how many words she can type per minute. So we're comparing two things, the weeks each week and then the words she can type per minute. And notice in this graph, we just have points. We don't have a straight line. We actually pick up our pencil each time. And this would not be a continuous graph. But instead, this is an example of discrete data. So really, this slide, we're not graphing anything. The big takeaway is I wanted you to see an example of discrete data or discrete relationships. And the big takeaway is that anytime you see points, you know that it's discrete. It's not continuous. We don't have one straight line connecting all of the points. So we don't have data for 1.5 weeks. We don't have data for 2.5 weeks. We only have data for, or each day really. We don't have data for each day. Even if we did, that would still be discrete. So we would be, anytime you're plotting points as data, it's discrete data. And you're gonna see some more examples of that this week as you go through your Schoology lessons. So again, continuous data, for it's continuous. The data is continuous over time. There's no gaps in our data versus discrete data where there is gaps. The data is presented as points. So I'm going to go to the next slide. So if you need more time, go ahead and click pause. All right, so moving on to a different idea where we're still dealing with relationships, but not in a graph form so much as we're looking at functions. So what is a function? So a function is a relationship between x and y's, but right now we're just going to focus on what makes something a function. And we can actually graph functions, but we're just going to be focusing for the next few minutes on what is a function. So a function is if you take an input, and our input in math is going to be our x values, and you get an output, which in math, our outputs are going to be our y values. So think of it as we're going to put a number into a machine, and then the machine's going to do something, that number, it's going to follow some type of pattern and spit a number out. So that is, you can think of that as the number we put in as our input, and the number that we get out is our output. So in this case, in our machine, it looks like if we put a 4 out and we get an 8, that our number doubled, right? So the pattern of what's happening inside is that we're taking 2 times our number. So let's keep going here. So let's keep going with our explorations of functions, and let's talk about what makes a function special. What makes a function, and separates it from just being an equation. So what makes something a function in particular, specifically a function and not just an equation? So a function, will not give back two or more results for the same input. So here we go. A function, if something is a function, it will not give back two or more results for the same input. So what does that mean? That means that if we put a 2 into our function machine, we're only going to get one result out. So if we have an input of 2, let's say our output is 8, that would be the only output that we could have. We couldn't put in a 2 and also get a 9. For each input, there can only be one output. A function is a set of ordered pairs in which each x input only has one y output. So that's kind of what I just said there. For every input, there's only one output. So I kind of said the same thing in 3 different ways, hoping that one of those will resonate better with you. So for each input, there's only one output. So again, if you put in a 2 into our function machine and it spits out an 8, that's the only output. We couldn't put in a 2 and also have it spit out a 9. That's just not possible. We can only have, for each input, we can only have one output. So we could not get like a 9 as an output. That wouldn't work. That would not work. We can only have one output for each input in order to make something a function. So hang on with me. I know that might be still a little confusing, but I'm going to help it make sense. Let's go on to the next slide. So another way that we can check a relation and see if it's a function and see if for each input there's only one output, because remember that's what a function is. For each input there's only one output. We can use what we call a mapping diagram. And here is an example of a mapping diagram. So remember, our inputs are always represented in our x values and our y values are represented by our outputs. I said that backwards. I want to say our outputs are represented by our y values. So what I've done here is here are x values and the corresponding y values. And I drew an arrow connecting the x value to its y value, or the input, and this would be our output. So if we put 0 into our function machine, and out would come a 6. If we put 1 into our function machine, out pops a 9. This input of 2 has an output of 8, and this input of 3 would have an output of 10. So because each of our inputs only has one corresponding y value or output, this is an example of a function. This is a function because for each of our inputs, there's only one output. So now from a mapping diagram, we can put each of these x and y values into ordered pairs. So remember, our inputs represent our x value. So when we write an ordered pair, we always do x, comma, y. So now let's put together all of our ordered pairs from this mapping diagram. So 0 goes with 6. So our coordinate would be 0, 6, showing that. Our next point, 1, our next is related to 9. So the input has an output of 9. And then we keep going there. 2 has an output of 8, and 3 has an output of 10. And you can see that each of our x values has one and only one specific output. So we did already identify, yes, this is in fact a function. So looking again at a mapping diagram, and mapping diagrams just are helpful in determining if number relationships are in fact a function. And I'm going to go on to the next slide, so if you need more time here, go ahead and click pause. Alrighty, so we've got a mapping diagram. The numbers on our left represent our inputs or our x values, and the numbers on the right represent our outputs or our y values. So let's start with using this mapping diagram to decide if this is a function. Let's decide if this is a function. So remember, to be a function, each input can only have one output. So look at this first number here, 2. The input 2 has an output of 1. I'm going to create an ordered pair here. And it also, here's another ordered pair. 2 is the input of 2 also has an output of 2. So this one input has 2 different outputs. Has 2 different outputs. So right away, because of that, we know that this violates the function rule, right? That each input can only have one output. This input has 2 different outputs. It's linked with 1 and 2. So because of that, this is not a function. This is not a function. Let's continue and write all the ordered pairs. So what would be the other ordered pairs? Well, 4 and 4. We've got 6 linked with 6. And we also have 10 linked with 4. And because we had our input here too with 2 different outputs, we determined this was not a function. And before we move on, so we use the mapping diagram to help us determine this was not a function, but we can also use ordered pairs. So if you're only given a list of ordered pairs, we can also use ordered pairs to help us determine if something is a function. So here I see that we have 2 of the same x values. So we've got 2 coordinates with the same x values, and then we've got different y values. So because we have 2 of the same x values and then 2 different y values, that lets us know that that is also not a function. So 2 different ways that you can tell if something is a function: look at the mapping diagram, or look at your ordered pairs and look for any repeating x values. And then if you do see any repeating x values, look to see if your y values or your outputs are 2 different numbers. And if your input is linked with 2 different outputs, you know it's not a function. So I'm going to go on the next slide. So if you need more time, go ahead and click pause. So we're going to switch gears now. And instead of talking about what is and is not a function, we are going to talk about domain and range. So these might be 2 new words for you. They might not. But let's talk about what is a domain and what is range. So domain, if you are asked to find the domain of something, you're being asked to identify all the possible x values. Whereas if you're asked to find the range of something, you're being asked to find all the possible y values. A quick reminder, when we plot points, we always plot the x coordinate first, followed by the y coordinate. Remember, your x coordinate tells you if you're going left or right, where the y coordinate is telling you if you're going up and down. So we are going to look at graphs and determine all of our possible x values, or our domain, and we can also tell somebody all of our possible y values, or the range. All right, so now let's go back and answer this question. It says, well, we want to determine the domain and the range from this graph. So let's start with the domain, and I'm going to change this color, the highlight. Let's do this nice blue for our domain. And remember, our domain is our possible x values, and our possible x values are going to be all of our possible horizontal, the location horizontally of our graph. So if we look at our graph, remember, we want to look at all the possible x values, and it ranges from, looks like -3. We can have x values that go from -3 all the way up to +1. So our domain looks like it ranges from -3, and it can go all the way up to +1. So our x values can be anywhere from -3, they can be any point, all the way to +1. But in math, we're going to write that notation a little bit differently. We're going to pull from Unit 1 and use a inequality to show that our x values can range anywhere from -3 to +1. But we're not just done quite yet. Look at how we've got an open circle here. Remember last unit, we learned that if we have an open circle, that means that it doesn't include the value of -3. So x can be greater than -3. We're not going to put greater than or equal to. Over here on the right side, we have a closed circle to show that x has to be less than or equal to 1. So our domain, the correct way to write it is using inequalities, would be that x has to be greater than -3 and less than or equal to 1. And that's our domain. That's showing the horizontal, all of our x values. Now let's talk about our range. We can keep that yellow here for our range. And our range is showing us the y values, all of our vertical up and down, right? So what are our possible values? So vertically, we can have any value from our y can be -4 all the way up to, we stop at 0. The graph, the highest it gets is to 0. So for our range, our numbers can go anywhere from -4 to 0. But let's write it correctly. Let's write it with an inequality. So range is all of our possible y values. And again, we've got a closed circle, so we can say that x has to be greater than or equal to -4, and it touches at 0 here. So I know that there is, so range from -4 to 0, it has to be less than 0, so that open circle there. So that is our domain and range. And again, make sure we want to write it as inequalities. So don't just do arrows to show, write it in an inequality format to show your domain and range. I highlight the correctly notated versions. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. And we are now ready for the week 6 key phrase assignment. So to get your credit for watching this recording, I want you to use what you learned in this recording to determine if we've got a mapping below, if the relation below is a function, and then why or why is it a function? Why or why not is it a function or not a function? And if you have any questions or need help with anything this week, please let me know. Have a great rest of your week.